Hey guys, sorry I can't be there today. Having to be on bed rest for a little bit. Just precautionary and make sure everything's okay. Here's the video lecture. It'll be broken up into a couple different segments, so it's not too long. And then there's also some videos for y'all to watch on A+ Physics. That goes over kind of the same thing, just from a different perspective. So instead of it being me lecturing, it's someone else. So the first thing we're looking at today is DC circuits, which is from chapter 19 from the textbook. So what we're really looking at is continuing on what we did last time. So the first thing you have are the circuit symbols that you're going to need to know. For the circuits, you'll notice you have a battery. The battery is represented by two lines, one being longer than the other one. The longer side of the battery is the plus side, and the shorter side is the minus side. Remember that current always flows from positive to negative, and so you'll need to make sure that you have those, you'll memorize that. So that way if it asks if the current's flowing clockwise or counterclockwise, look from the longer side of the battery back to the shorter side. The one for the capacitor you don't really need to know, that's not covered in AP1. If you take APC, AP2, you'll see more about capacitors then. The resistor is like the little heartbeat that you see there on the screen. And it doesn't matter how many like peaks and valleys you draw. It's not like a vector where the more you draw, the stronger the resistor is. You'll just label it. So just draw however many you want, 2 or 3, 4, whatever. Just be consistent. Your wires are going to be just straight lines. Okay, normally whenever we draw circuits, we always draw them being nice square boxes, so your wires are always going to meet. If you're trying to bend it down to another part at 90-degree angles, your wires never cross, and they must be solid straight lines. The next one is a switch. You'll notice the switch is actually open, which means the current's not flowing because there's a break in it. So this case you have an open switch there. An open switch means the lights are off. If it was a closed switch, it would just look like a normal wire. Then the last one you have is the ground. I prefer the drawing on the left where it has the 3 lines underneath it. If you think about like the outlets, the 3-prong outlets, that at bottom prong is actually the grounding, and it does the same thing like we talked about with induction, where grounding is going to pull those excess charges off, so it's a lot safer for you to run. So I prefer the grounding one on the left, which so does College Board. So make sure you memorize those. You're going to need to know how to draw them, and as well mostly how to interpret the circuits. Okay, so we've talked about batteries before, and within a battery, though, as we talked about it as being like this perfect source of energy per charge. Okay, however, it's not. Okay, so what we have is this idea called an EMF. EMF used to stand for electromotor force. However, now it doesn't really stand for anything. We just call it EMF because at first they thought it was a force moving the electrons through a circuit, and then of course we know that it's not a force, it's the energy per charge, or the volts, that moves the electrons. So they've gotten away from calling it electromotive force and just shortened it to EMF. EMF is represented by this cursive letter like E that you see at the end. I just always write it as a cursive E. And it's always measured in volts. So what happens when you're looking at a battery is that a battery actually has a little bit of resistance in general. So your EMF is actually the ideal amount that a battery can operate off of. So if your battery is 12 volts, your EMF would be 12, but in reality you're not going to get a full 12 volts from the battery. You're going to get a little bit less than that. So VAB is actually looking for the voltage of the battery itself. So from the positive to negative, positive side being A, negative being B. E is going to be your EMF, still measured in volts, and then I is going to be your current running through the circuit, and then that lowercase r is going to be the resistance of the battery. So the battery in and of itself is going to slow down the electrons just a smidge naturally. So that lowercase r is going to be the resistance of the battery with it. So when you look at a battery, okay, here you have the positive side. The positive side is always going to be A. So if you look at how you're drawing your battery in the middle with the source of EMF, the longer side of the battery goes to the A, and the negative side is B. That's a standard convention. So Your VAB is your terminal voltage, or the voltage on the battery. And then you have this resistor inside in the middle, so that's your internal resistance. And then this cursive E represents your EMF as you're going through it. Again, your voltage AB, or your voltage of the battery, is going to be a little bit less than the EMF. So it's saying what is the actual energy that's coming out as opposed to the ideal. Like if there wasn't any internal resistance, all things would operate at their maximum capacity. But again, that's not possible. Next thing that you have to look at are your resistors in series. Okay, so anytime you have resistors in series, what that means is that there's one path to go from positive to negative side of the battery. Okay, so here you have your circuit, your battery's down at the bottom. Again, that positive side being longer than the negative side. Current's going to go from positive to negative by standard convention. So you're going to have a current running through each one of the resistors. And since you have to pass through all the resistors, your resistance is, or your current is going to be the same in each resistance. Okay, think about it as follow the leader. You can't go, if you're in the middle, you can't go faster than the person in front of you is going. Okay, so it's whatever pace the first person's moving, that's how fast the entire line is going to go. So in a series circuit, your current is the same at every single point. Okay, so it doesn't matter if you're looking at the current before the first resistor, in between the second, first and second, in between second and third, after the third, your current is going to be the same at every single point. Okay, as you go through it. So you have to go through all three resistors. What that means, again, is looking at the fact that your current is the same. However, your voltage is not. So within it, as you pass through each resistor, you're going to use a certain amount of energy. So that means you're going to use a little bit of energy going through resistor 1, a little bit of energy going through resistor 2, and a little bit more energy going through resistor 3. So each time you go through the resistor, if you're talking about a 9-volt battery, the first one would use a couple volts. And so then the next one would only have that 7 volts now left to use for energy. It's going to use some energy, and then the third one would use the rest. So here you have an equation to find your total voltage. So your total voltage, or your V over here, this would be the voltage of the battery, is going to be equal to the voltage of through the first resistor plus the second resistor plus the third resistor. So each one is getting it. If your resistors are the same size, then those three voltages will be the exact same. So it would be like if you have a 9-volt battery, your resistors are the same, then each resistor would have a potential difference running through it of 3 volts. Okay, and then again, since you look at the equation for Ohm's law, V equals IR, so V1 would be equal to I times R1, because the current's going to be the same through everywhere. So what we can say is that we get an equation to find our resistors in series, which is your equivalent resistors wants to say, instead of having 3 separate resistors, how much would I have if I just had one resistor? So to find up your total resistance, your equivalent resistance is just your total resistance. You would do R1 plus R2 plus R3. So just add them up, okay, whatever it is. Your REQ is always going to be measured in ohms, just like it was for regular resistance that you'll see. So REQ is just, instead of having multiple resistors, just one resistor. In a series circuit, if one light bulb goes out, all of them will go out. So if you've ever had a strand of Christmas lights, one light goes out and the entire thing goes out, you have no idea which one is actually burnt out. That's a series circuit. We talked about circuit breakers last time. It's how one would trip and then everything would trip on that same one. Those are all wired in a series because they're all going off the same one. They're still in combo, which they're actually in combination, but there's a portion of it that's wired in series. So if one goes off, they all go off. Okay, if your resistors though are in parallel, parallel means that you're having multiple pathways. So your current is going to go from the positive side, it's going to hit a point, and it's going to separate. So you're either going to go through resistor 1, resistor 2, or resistor 3. And they're each going to act as their own separate circuits of each other. So whatever happens through R1 does not impact R2, does not impact R3, okay, as you're going through your circuits. So within it, think about it as traffic. Okay, when we think about adding more resistors, you're going to slow down the current. And in a series circuit, that's true. Okay, so you're adding it up to find REQ. In a parallel circuit, though, since your current is going to hit point A and then it can split and either go through 1, 2, or 3, as you add more resistors, you're actually going to be decreasing the total resistance and increasing the current. Think about it in terms of traffic. Right now you have Derry Ashford just south of Memorial, in between Briar Forest. It's shut down to 1 lane in each direction. Okay, traffic's backed up there all the time. If they would open it back up, okay, 2 lanes in each direction, now there's more places for the cars to go. So there's going to be a lot more flow of traffic, so you're not going to be stuck behind, so you'll move through faster. If they made it into 3 lanes in each direction, the same thing. You would be adding another pathway for the current to flow through, so you're going to speed up how fast the electrons can move through the circuit. So what you have is that your total current is the sum of the currents in each resistor. So each one's going to be going through their own pace. Again, you've sat in traffic before and you'll notice like the left lane's going really fast, the middle lane's going in the middle, and then the right lane's going really, really slow. So since they're all on their own pathways, they can each have their own speed or each have their own current. So the current is going to be different. To find the total current in the whole circuit, add them up. However, your potential difference or your voltage is going to be the same in each part since each one is their own circuit. So that 9-volt battery is going to give 9 volts to the top resistor. It's going to give 9 volts to the middle resistor and 9 volts to the bottom one because they're each on their own separate path. So it's like 3 separate circuits jammed together. To find your total resistance, you would use the equation 1 over Req equals 1 over R1 plus 1 over R2 plus 1 over R3. Just be careful on this equation. If you are not good with fractions, don't use fractions. Okay. Also be careful that the value that you're solving for is in the denominator. And so that means you're going to want to have to inverse it. So whatever your answer is. If your answer is 5 over 2, then your answer would become 2 over 5, okay, and vice versa. So just make sure that the variable that you're solving for, since it is in the denominator, make sure you inverse your answer, whatever it is. Please, for this, again, if you're not comfortable with fractions, don't use fractions. Every year I get someone, they'll add 1/3 plus 1/3 plus 1/3, and give me an answer of 3 over 9, which reduces to 1/3. Okay, please don't be that person. So if you're not good with fractions, just don't use them. No big deal. Okay, so that's it for this part of it. I'll start working through some problems and continue on with the notes.